Folks, in this video, we're talking about heat capacity. What is that? I don't know. Let's find out. On my way, cat. So we got a few objectives here. I want you to be able to explain how heat flow relates to temperature changes, and also I want you to be able to define heat capacity, and then do some calculations using this fun formula, which we'll talk about later. So let's get into it. Heat flow and temperature. Well, heat is energy. And temperature is a measure of the kinetic energy or motion of particles inside a substance. And so when heat flows into a substance, the particles will start to move faster. So in other words, heat flowing into a substance increases the temperature of that substance. So hot metal and cold water. Oh, virus protection, ruh-roh. So let's imagine we have a piece of hot metal and we place it into a container of cold water. Well, heat is going to flow from that hot metal into the water. This is going to cause the temperature of the metal to decrease as the temperature flows out of it. It's going to cause the temperature of the water to increase as the temperature flows out of the metal and into that water. Here's our cooled down metal, and the water's the same color. So eventually the water and metal are going to reach the same temperature. When they are the same temperature, we're not really going to see heat flowing between them anymore. Because they're at the same temperature, aren't going to have heat flowing between them. So heat capacity. Well, before we talk about that, let's do a little thought experiment. Imagine you have masses of water and iron, liquid and metal. The iron is heated to 100 degrees Celsius and the water is cooled at 10 degrees Celsius, and then we put the iron in the water. Okay, imagine at the same time, you've got another set, equal mass of iron water. Now we've got the iron, it's cold metal, and put it in hot water. In which case, situation A or B, or you think we're going to have a higher temperature? Or do you think in both of these situations we'll end up with the same temperature? Pause the video and think about that. Well, it turns out in situation A, we're going to end up with a pretty low temperature. Water's only going to cool up a little bit. And in situation B, the water is only going to cool down a little bit. So that's pretty wild. This is because the reason we don't end up with the same temperature in both of these situations is because iron and water have different heat capacities. Well, heat capacity, what is that? It's the amount of energy it takes to increase the temperature of a substance. So since water has a much higher heat capacity than iron, water is going to cool down in the second situation pretty slowly while the iron heats up a lot. As that water gives energy to the iron, the water's temperature goes down a little bit. The iron temperature goes up a lot more. That same amount of energy moving around. Let's look at this a little bit further. So when we measure heat capacity, we're going to measure how much energy is required to raise the temperature of 1 gram of substance by 1 degree Celsius. So we're going to look at 1 gram and temperature raised 1 degree Celsius. How much energy do you need for that? And so we're going to measure energy in joules. And the units we're going to see on heat capacity are these. Joules divided by grams times degrees Celsius, or joules per gram times degrees Celsius. So we've got grams and degrees Celsius in the denominator here, joules in the numerator up top. So we want to measure how temperature changes with heat capacity. We're going to use this fun equation. Q equals mc delta T, or I like to call it Q equals mcat. So in this Q is equal to heat flow, or the energy that's moving around. M is our mass. C is our specific heat. Delta T is our final temperature minus our initial temperature. Delta means change. I should mention, every different substance that we look at is going to have its own unique heat capacity. So knowing the heat capacity, or the specific heat rather, for a substance will be helpful. Neat. Great. So, blah, blah, blah. The temperature we're going to measure in Celsius, the mass we're going to measure in grams, and the energy we're going to measure in joules. Nifty. And so I realize I'm saying specific heat here and heat capacity. We're going to kind of use those interchangeably. So let's do an example problem. How much energy is needed to heat 15 grams of water by 12 degrees Celsius? Here we have the specific heat of water given to us. Well, to do this, we're going to want to just plug into our fun equation. And I like to take a little inventory of all these different variables so that we can plug them in really easily. We don't know Q. We're being asked to find the energy. So that's our question mark. We do know the mass, that's in the problem. And we do know the specific heat that's given to us. We also know the change in temperature. We know it's going up 12 degrees Celsius. So our final temperature will be 12 degrees higher than our initial temperature. So I can just plug these into my equation. I can plug in M, C, and delta T right into this equation, like I've done over here. And I can just multiply those dudes together to get the heat that's required to raise 15 grams of water by 12 degrees Celsius. Neat, neat, neat. Well, let's look at a few more practice problems. Here's another one. In this one, we want to, how much energy is required to heat 96 grams of iron from 17 degrees Celsius to 359 degrees Celsius. And here is our specific heat. Why don't you pause the video and using your notes on that previous slide, see if you can solve this problem. Sweet, well, let's go through it together. So again, I'm going to look at my equation. I'm going to take a list of everything I know and what I want to know. I'm asked how much heat, so I don't know how much heat or Q is going to be flowing around, but I do know the mass, it's 96 grams, and I know the specific heat that's given over here. And delta T, I can figure that out really quickly. It's T final minus T initial, so here's my final temperature, and I'll subtract from that initial to get delta T of 342 degrees Celsius. And so now I just plug all those into their spots in the equation, and I can multiply all these pups together and solve for Q. Let's do one more problem. This one's a little bit spicier. In this one, we've got 202 grams of water at 70 degrees Celsius, and it loses 500 joules of heat. What's the final temperature going to be? Well, we're going to approach it the same way. Here's our equation. And so we know Q, we're losing heat. So that's negative heat. Heat we're giving away. So that's negative 500 joules. And we've got our mass. And delta T, oh, we've got our specific heat. Sorry. And delta T is a little funky here. We know the final initial temperature. We are looking for the final temperature. So we're just going to leave it like this. Oh, that guy's hiding it now. Check that out. We're going to leave it in that form and just go ahead and solve the problem that way. It's going to require a little bit of extra mathing. That'll be fun. So here's all of those plugged into the equation. And so what I'm going to do is I've got these two dudes times this fraction. And so I'm going to distribute those into my fraction. Here I've done that and I've broken it up into these two dudes times the final temperature minus these two dudes times my initial temperature of 70 degrees. And so I can just solve for this section. And since it's subtracted, I can add this to each side to eliminate it from here and move it over here. And so now I can just divide each side of the equation by 22 grams and 1.186 joules per gram degree Celsius. What I will do is isolate the final temperature. I can solve for that, and that's going to be 64.6 degrees Celsius. So that was a little bit of a spicier problem. But hopefully you feel pretty cool about heat capacity, and yeah, you can do some math with that Q equals MCAT. Sweet. Well, I hope you enjoyed this video, and ta-ta. Have a great rest of your life.